Good morning, student. So today we are going to start our topic vector space, which is unit 4. So first of all, what is a vector space? As we have already discussed number system in one dimension, like natural number, whole numbers, then the integers, rational number, and real number. So that is number in one dimension. When we move from one dimension to higher dimension, like two dimensional, three dimension, or higher level of dimension, that becomes a vector space. So what is this? We move to a higher level of abstraction. A vector space is a set with addition and scalar multiplication that behave appropriately like r raised to power n. R raised to power n means it has n dimensions of over the real numbers. Like if it is a 3 dimension, we have 3 coordinates x, y, z. Same way it will have n dimension, x1, x2, x3 up to so on xn. So these kind of components are known as vector space element. Further, just like simple number, vector space also hold the scalar addition, scalar multiplication and vector addition. So a vector space V is a non-empty set equipped with an addition and a scalar multiplication operation such that for all alpha and beta belongs to real number and for all u, v and w belongs to vector space. Now here alpha and beta are simple scalar number, like it could be 1, 2, 3, 4, 5, and u, v and w, these are the elements of vector space. If a vector space is of 3 dimension, it will have 3 components. If vector space is of 2 dimension, it will have 2 components. So there are few properties which a vector space holds. These properties are similar to the property which a single number holds. First is closure property, closure under addition. So when we are going to add any two vector u and v, the resultant vector should also belongs to v. That means the resultant vector when after adding u and v should also be the member of vector space v. This is called closure property. In commutative property, we have already discussed in our earlier classes is that u plus v is equals to v plus u, and associative property is you can add u plus v and the resultant vector you can add with u, or you may add u with v and the resultant vector can be added with the w. This is known as associative property for addition. After that, we have a existence of identity. Now what is an identity vector? Identity vector is such a vector when it is added to any vector, it will not change the vector. For example, which vector should I add with 1, 2 two-dimensional vector so that the answer is again 1, obviously we are going to add here 0 vector, which is 0, 0. So such kind of vector are known as identity vector or 0 vector. The next we have inverse vector, or you can say negative. So what is inverse? Inverse is such a vector which we are going to add with any vector. The result we are going to get is identity element, which is 0 vector. For example, if I have a vector 1, 2, which vector should I add with 1, 2 to get 0, 0 is minus 1, minus 2, right? So if you are going to add 1, 2 with negative of 1, 2, which is minus 1, minus 2, the result will be 0. So this is called existence of inverse. And for every element, for every vector, there will be a unique inverse of negative of element. Next we have closure under scalar multiplication. That means if I am going to multiply any scalar number with a vector number, the resultant will be again a element of vector space V. This is distributive law. Now we are going to distribute a scalar a over two vectors u and v, and this will be equals to a into u plus a into v. Next again a distributive property is a plus alpha plus beta. Now here alpha and beta are scalar and v is a vector. So same like vectors are distributed, we can distribute scalar also. It will be alpha v plus beta v. And this is associative property for vector multiplication. Then we have unity element of vectors. Unity element 1 multiplied with any vector will be equal to vector itself. Then we have a vector v is equals to, then there are few examples of a vector space. Here v is a vector space which is a 0 element. Then next is the set of all m into n matrix. So any set of matrix whose dimensions are m comma n, means which has m rows and n columns, could conclude any vector space of dimension of matrix. Next we have a definition of a linear combination. So what is a linear combination? For any vectors v1, v2 up to so on vk in a vector space V, any vector v of V's vector space V could be written as alpha 1 into v1 plus alpha 2 into v2 plus dot 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 alpha n into vn. So this is known as a linear combination. This can be called as that vector V is written as a linear combination of elements v1, v2, v3 and vn, where a1, a2 up to so on ak are the coefficients of vector space. You can see here we have example. Suppose f is a vector space from real number to real number over quadratic equation. F could have a quadratic equation. So if 2, 3 and 4, this can be taken as scalar number, then what are the vectors? First vector is x square, second vector is x, and third vector is constant, which is 1. So this vector f can be written as 2 times g, 3 times h plus 4 times k. So here x square, x and 1 is vectors, 2, 3 and 4 are constant. So you can take this example up to any degree of polynomial. You can take cubic, any nth power of polynomial. Such kind of examples are known as vector space. Then we have a subspace. So as we have earlier discussed set theory, in set theory the smaller part of a set is known as subset. Similarly, in vector space, any smaller subset of a vector space V is known as subspace W. So if you have a vector space V, it's a non-empty subset W, which again can become a vector space holding same operation of addition and scalar multiplication as V. If it also satisfies the condition to become a vector space, then W can be called as a vector subspace. Now let V be a vector space, then a non-empty subset W of V is a subspace if and only if it is closed under addition and scalar multiplication, which means if I am adding any two vectors from vector space, the resultant will also be again element of vector space. If I am multiplying any scalar number with a vector, the resultant will again be a element of the vector space. So any subset of vector space, if satisfies these two conditions, then it will be known as a subspace of a vector space. Now suppose we have any example. The question is, show that W, which is a comma b comma 0, where a and b belongs to real number, is a subspace of V3 over R. So let W is this. Here the condition is given that first element and second element of W should belongs to real number, and the third element should be 0. That means x component and y component are non-zero, and the z component should always be 0. Now definitely this is a subset of a real number over 3-dimensional real number. Now we will check the conditions for this element to for this subset to become a vector space. First is it should be non-empty. Obviously 0 vector of 3 dimension is 0 0 0. It will always be an element of W, hence this is a non-empty set. Second condition we need to check over here whether it is closed under addition or not. To check this condition, we will consider two vectors u and v. How to add vectors? Add first component with the first one, it will be a plus c. Add second component with the second one, it will be b plus t, and the third component is 0 plus 0 is 0. Now their sum will be definitely a non-zero element, and which will again further belongs to W. So this element is closed under addition. Now let us check the property for closed under scalar multiplication. For that we have to consider a scalar number lambda, which is an element of real number, and u is a vector which is a comma b comma 0. Now if we are going to multiply any scalar number with a vector, it will be simply lambda into a, lambda into b, and the last element will be lambda into 0, which is nothing but 0. So this new element again satisfies the condition. What the condition of to become the element of W is, first two members should be non-zero and the last one should be 0. So we can see here it satisfies the condition to become the element of W. Hence W is closed under addition and scalar multiplication, and W is a subspace of three-dimensional vector space over real numbers. Now this is one more theorem which we can use for any subset W of a vector space to check whether it is a subspace or not. For that you can take two scalars and two vectors. U and V are vectors, alpha and beta are scalar. Sorry. If alpha into U plus beta into V belongs to W, then definitely it will be a subspace of vector space. The next is a very important definition for the vector space. It is linearly independent and linearly dependent vector spaces, subset of vector space. So for linearly independent and dependent, simply suppose you have given a set of vectors v1, v2, v3. Simple. Take the linear combination. Consider if you have three vectors, consider three scalars. Let it is alpha 1, then take alpha 1 beta v1 plus alpha 2 v2 plus alpha 3 v3. Take that linear combination equal to 0. On simplifying that system, you will get a system of equation. We will solve that system of equation. If all of the scalars are 0, then the given set of vectors is known as linearly independent. But if any of the scalar is non-zero, any means even if one scalar is non-zero, that will be known as a set of linearly dependent set. As you can see here in the definition, let V be a vector space, V1, V2, Vk be any set of vectors. Then we will write this combination as a linearly independent if A1, V1 plus A2, V2 dot dot AK, Vk, linear combination 0 gives you all of the scalars are 0. Otherwise, if any of the scalar is non-zero, this set of vector will be known as linearly dependent. Let us see few examples on the same. So question is, examine the following system of vector for linear dependence. If dependent, find the linear relation between them. So here we have provided three vectors v1, v2, v3. Let us consider three scalar a, b, c. Write their linear combination equal to 0. So a into v1 plus b into v2 plus c into v3 equal to 0. So a into 1 minus 1 1 plus b into 2 1 1 plus c into 3 0 2. Let this equal to 0. Now multiply a, b, c with their individual brackets and add first component. So this will be, first equation is a into 1a plus 2b plus 3c is equals to this 0. Second equation will be minus a plus b plus 0 equal to 0. And the third equation will be a plus b plus 2c is equals to 0. So here we get the system of equation. Now we will solve this system of equation to get the values of a, b, c. If any of the value is non-zero, this system of vector will be linearly dependent. Otherwise, if all of the values of a, b, c are 0, it will be linearly independent. Let's see. So here solving second equation, we get that b is equals to a. Now you can put this b is equals to a in equation 3 and equation 1. We get that c and b, they both depend upon a. So definitely this is a non-trivial solution, which means if that means you can simply say that b as well as c, they both depends upon scalar a, right? So if you are going to take that a is equals to t, then b will be t and c will be equals to minus t. Put in the starting equation. Here you can see that v1 plus v2 minus v3 is equal to 0. This is a relation between them, which means a is non-zero, b is non-zero and c is also non-zero. Hence this given set of vectors are linearly dependent. In next example, we have set of vectors v1, v2, v3 and we have to show that these are linearly independent. That means when we are going to solve their system of equation, the scalar a, b, c will be definitely 0. So let this is v1, v2, v3, a, b, c are three scalars. Now a into v1 plus b into v2 plus c into v3 is equals to 0. First of all, we have to write the linear combination. Put the value of v1, v2 and v3 here. Then make the system of equation. So it will be a plus 0 plus c. The first equation is a plus c is equals to 0. Second is 0 plus b plus c is equals to 0. The second equation is b plus c is equals to 0. And the third one is a plus b plus c is equals to 0. Hence the third equation, z component is a plus b plus c is equals to 0. So this is the system of equation. From first equation we can get that c is equals to minus a, and the second equation we can get that c is equals to minus b, which means minus a is equals to minus b. This implies a is equals to b. You can cancel minus with minus, a is equals to b. Now you can substitute this value of c and b in equation number 3. We get a plus a 2a minus a is 0. This implies that a is 0. Now a is equals to minus c and c further is equals to minus b, which implies a, b and c, all three are 0. Now we get that all three scalars are 0. Hence the given set of vectors v1, v2, v3 are linearly independent. So simple condition is there. If all of the scalars are 0, it will be independent. If any one of the scalar is non-zero, it will be dependent set of vectors. Thank you.